Aqueous solutions turn up a lot in the chemistry laboratory. Many times when we react chemicals, we dissolve the chemicals in water. When a chemical is dissolved in water, it's what's known as an aqueous solution. Dissolving the chemicals in water helps them react more quickly. The water separates the chemicals into individual molecules or ions, and also because of the movement of the water molecules, the ions or individual molecules are able to move and they come in contact with each other more frequently, so the reaction speeds up. Now, ionic compounds and acids do something known as dissociation when they dissolve. What this means is they break apart into the ions that make them up. Now, not all ionic compounds are soluble in water, but if they are soluble, they're going to break apart into the ions. Now, when polyatomic ions dissociate, they retain the integrity of the polyatomic structure. So here we have a depiction of sodium chloride dissolving in water. Each ion is separated and completely surrounded by water. And of course, these are enlarged trillions of times. The individual ions are very, very small and actually kind of fit between water molecules. Here's silver nitrate dissolved in water. Each silver cation is surrounded by water molecules, and each nitrate anion is surrounded by water molecules. Again, this process where an ionic compound or an acid breaks apart into its ions is known as dissociation. Let's look at some pictorial representations of dissociation. Here we have potassium iodide. When you see potassium iodide AQ, that means that potassium iodide is dissolved in water. It means we're talking about a solution. Now really, because this is an ionic compound, and we know this because it's a metal and a nonmetal, it exists as the separated, dissociated ions. So this is really the way that it exists in solution, K plus AQ plus I minus AQ. Let's look at a polyatomic ion example. Here we have copper sulfate, copper 2 sulfate. When we see copper 2 sulfate AQ, what that means is our copper plus 2 cation is completely surrounded by water, and our sulfate is completely surrounded by water. In solution, ionic substances exist as the dissociated ions. Now let's look at an example where we don't have a 1-to-1 ratio of cation to anion. Here we have 2 potassiums for 1 sulfate. Why is that the case? Well, sulfate has a -2 charge, potassium has a +1 charge, so 2 potassium cations are necessary to cancel out the -2 of the sulfate. When we see potassium sulfate AQ, what that means is that our 2 potassium cations are dissociated, each completely surrounded by water, and our sulfate is dissociated, completely surrounded by water. Now these two are written together, but they're really nowhere near each other because like charges repel. Now let's look at a definition, electrolytes. Electrolytes are substance that when it's dissolved in water conducts electricity, and it conducts electricity because of the presence of ions. So electrolytes, when they dissolve, form ions. So that definitely would be an ionic compound, because when an ionic compound dissolves, it forms ions. Now this little picture here is a setup that's often used in demonstrations. We have a light bulb connected to a battery with 2 electrodes. If these electrodes were placed in an electrolyte solution, the ions would allow a current to flow and the light bulb would light up. Here the electrodes are in pure water, which does not form ions when it's dissolved. It's a non-electrolyte, so therefore the light bulb is not lighting up. Now there are 3 types of electrolytes: strong electrolytes, non-electrolytes, and weak electrolytes. In strong electrolytes, the total compound that's dissolved dissociates completely into ions. Everything that is dissolved is an ion surrounded by water. And this is all dissolvable ionic compounds. In non-electrolytes, none of the molecules separate into ion, and this is typically most covalent compounds. So here we have sugar molecules, and again, these are enlarged trillions of times. Sugar molecules dissolved in water, these don't dissociate. They are covalently bonded, no charges here. They remain as individual molecules. They would not light up a light bulb. And then in a weak electrolyte, there are ions that form, but just a very, very small percentage of them. So let's look at examples of these. Salts is another word for ionic compounds. If an ionic compound is water soluble, then it is a strong electrolyte. All the ions dissociate. Acids, we know from our naming, have H plus in them. When they dissolve in water, they form H plus as well as some other anion. If we're looking at binary acids, such as hydrochloric or hydrobromic acid, the anion is monoatomic, such as bromide, if we're talking about hydrobromic acid, or chloride, if we're talking about hydrochloric. In oxyacids, the anion is the polyatomic ion, whose the name is based on. Acids all have sour tastes. Many of them react with and dissolve with many metals. And strong acids are strong electrolytes. They completely break apart into ions. And weak acids are weak electrolytes. They only partially dissociate into ions. Now similar, or kind of opposite an acid, is a base. A base forms OH minus hydroxide when it's dissolved, whereas an acid forms H plus. Waters have a bitter taste, kind of like soap. Soap is basic. They have a slippery, soapy feeling. They also have weak and strong bases, but they're not as easy to talk about as the acids are.